Hello, everybody, and welcome back to this short course on quantum computing. So basically, today we're going to discuss a very interesting topic, which is quantum entanglement. So before delving into the details, let us imagine a situation where we have Alice and Bob as two individuals who are sort of separated by millions of light years. Now, is it possible for anything that Alice does in her life to have an impact on Bob's life? And the vice versa as well, whatever Bob does has an impact on Alice's life. So this more or less sounds like fiction, right? However, this is not necessarily a fiction, for this is a reality in the world of quantum. So in the quantum domain, it is possible for two such particles to be sort of entangled in a way, even though they have no direct interaction with each other. They have no exchange of energy. They are separated by maybe perhaps millions of light years. Yet, whatever that happens to Alice has an impact on Bob, and whatever happens to Bob has an impact on Alice. And when such a thing happens, Alice and Bob are said to be entangled, right? So now, since so far we have talked about qubits, we will talk about quantum entanglement from the point of view of qubits. So let's assume that Alice has a qubit and she is measuring it in her own orthonormal basis set, that is ket A0 and ket A1. Bob has another qubit which he prefers measuring in his own orthonormal basis sets, that is ket B0 and ket B1. Right? So for Alice, we can sort of express the qubit, that is ket V, as a linear superposition of her basis sets, that is C0 A0 ket plus C1 A1 ket. Right? And similarly, Bob's qubit can be defined as, or rather expanded as, ket W, which is equal to D0 ket B0 and D1 ket V1. Fine. Now, to understand the aspect of entanglement in a very easy manner, using the mathematical formulations we had gone through, we take the tensor product of, ket V and ket W. So what's a tensor product? A tensor product is basically nothing but a multiplication of these two vectors. And if we just take the multiplication of these two vectors and sort of expand it in terms of their corresponding eigenvectors, this is the expression that we have. This is the expression that we have. So the first term is C0 D0 times ket A0 ket B0 and so on and so forth. Right? So the physical significance of the first term is the probability of the event. And the event in this case is Alice measures her qubit and it collapses to A0 with probability C0 square, and same thing done by Bob simultaneously results in his qubit collapsing to ket B0 with probability D0 square. And I hope you can similarly define significance of each of these terms as well. Right. So this is basically the tensor product expansion. Now, if we consider this example that C0 B0 is 1 by 2 root 2 and C0 D1 is root 3 by 2 root 2 and C1 D0 is 1 by 2 root 2 and C1 D1 is root 3 by 2 root 2. If we just take, there's nothing special about these numbers, we're just taking this numbers to just as an example to show something to you, right? So I'm sorry. So this is a slide. So when we have such a form of the tensor product, you can do a very basic algebraic calculation to sort of factorize these two, this equation into the product of these two terms. That is 1 by root 2 get a naught plus 1 by root 2 get a in 1 multiplied by 1 by 2 get b naught plus root 3 by 2 get b1. Right? What is the meaning of this expression of this tensor product? Why have we been talking about this? So let us understand. Let us understand Alice makes the measurement first. She has her qubit. She's in her own universe, and Bob is in his own universe. They don't know each other. They have no exchange of energy with each other. She has her own qubit in her own orthonormal basis, and Bob has his own orthonormal basis in his own universe, and we took the tensor product of that, and we had been given the values of C1, C0, D1, D0, and we arrive at this expression. We are able to factorize this. So this tensor product is factorizable. And what happens over here is that, let's say now Alice measures her qubit first. Okay. Say she measures her qubit first, then she has a probability of getting A0 as her collapsed state. And that probability is half, and the same thing for her state to collapse to get in 1, that is again probability half. None of it impacts Bob's qubit. So irrespective of what result Alice got post measurement, the probability of Bob's qubit when he measures his qubit later on of collapsing it to get B0 is 1 by 4, and the probability of it collapsing to get B1 is 3 by 4. Right? So irrespective of the fact whether Alice's qubits collapse to A1 or A0, the probability of Bob's qubits collapsing to B0 and B1 does not change. Similarly, you can do a thought experiment wherein Bob does the measurement first, and irrespective of what state of Bob his qubit collapses to, the probability of Alice's qubits collapsing to A1 and A0 remains the same when she makes a measurement after Bob. So in that case, what's happening is that Alice's qubit is not entangled with Bob's qubit because the measurement does not impact each other. There's no relation. We took the tensor product, we were able to factorize it. And when we are able to factorize the tensor product, that is when we can tell that the two qubits are unentangled. Right? So I hope the concept of two qubits not being entangled is more or less clear from the context of tensor products. Now, considering another example, now the values of the coefficients are different. So now when we try to factorize this, we can't factorize this. Right? So what we do is that we try to express this term in terms of Alice's perspective. So we take get A0 common, and this is Bob's qubit, and then take get A1 common, and this becomes Bob's qubit. So what is the difference between this expression and this tensor product? Right? This is not factorizable. Moreover, what we can see is that Alice's measurement impacts the outcome of Bob's measurement. How so? In the sense that if Alice has a probability of getting A0 or A1 with 50-50 probability, as you can see, say it collapses to A0. There's a 50% chance it will collapse to A0 when she measures first. In that case, right, this term is 0. This whole term is gone. So we have only this term. So this becomes Bob's qubit. Then in that case, his probability of the thing collapsing to B0 and B1 are same. However, if Alice's qubit had collapsed to A1, then Bob's qubit would always collapse to B0 and never to B1, which means that the measurement of Alice's qubit impacts Bob's qubit. So whatever Alice does with her qubit and whatever happens to her qubit post measurement, whatever state it collapses to, has a direct impact on Bob's qubit. The same thing can be realized by talking in terms of Bob's perspective, wherein you take get B0 common and get B1 common, and this becomes Alice's qubit when Bob's result collapses to B0, and this becomes Alice's qubit when Bob's eigenstate collapses to B1. So basically the probability of Bob's qubit collapsing to B0 when he measures first is 3/4, and collapsing to B1 is 1/4. So when the former happens, the probability of Alice's qubit when she measures later on is 1/3 of it collapsing to A0, and of it collapsing to A1 is 2/3. But if Bob state collapses to B1, then Alice will always get the collapse state as get A0 and never will get A1, right? So in this case, the difference between this case and the previous case is that Alice and Bob's kit, or the qubits, are entangled depending on who measures first and what state it collapses to will have impact on the other person's qubit when he or she measures later on, right? So this is the general understanding of quantum entanglement, and in the later lectures we will discuss about the applications of quantum entanglement in terms of quantum cryptography. So I hope you have found this part quite interesting. There are various tutorials available on YouTube. There are different contents available on YouTube. You can just have a look. There are many visual representation of entanglement that can sort of convince you more about this concept, right? So I want to thank you for watching this video, and hope to see you in the next lecture soon. So thank you very much for watching. Have a good day.